Hello and welcome back to day 7. As we'll see today, the algorithm isn't complex in terms of the amount of code. It is a little tricky today. Not sure that we have a whole lot of refactoring going on. So maybe if we have extra time left over today, we can, for the first time, put in some of the edge cases and the guard clauses and things like that we've been sort of skipping and leaving for another day. Maybe today is another day. So let's see how we do in terms of time. Okay, getting started for day 7. Historians take you to a bridge. When you go to cross the bridge, there's engineers trying to repair it. You won't be able to cross till it's fixed. You ask how long it'll take. Engineers tell you they only need to be able to find the calibrations, but some young elephants were playing nearby and stole all the operators. I don't understand that, but sure. Finished calibrations if only someone could determine which test values could possibly be produced by placing any combination of operators into their calibration equations. Sounds like that's what we're going to do. All right, so here's the input, right? So we have a target number and we have values, and we're going to need to figure out what are the operators that could go in here that could potentially give us the target value. Each line is a single equation. It's your job to determine whether the remaining numbers can be combined with operators to produce test value. Operators are always evaluated left to right, so no precedence rules. Furthermore, the numbers can't be rearranged. Okay, so we have to take them in order. Glancing into the jungle, you can see elephants holding 2 different types of operators, add and multiply. Fair enough. Only 3 of the equations can be made true by inserting operators. Obviously, that first one, 190, 10 times 19 is 190. So if you put in multiplication in there, that's going to work. 2 positions for the operators. This one's kind of interesting. You can do plus and times or times and plus and get the right answer. That actually doesn't matter so much. That's just a coincidence. Excuse me. And then lastly, plus times plus gets us to 292. So they want to know the total number of all the ones that are valid. So 3749, that's valid. 193, 3267, 292, that's valid. Okay, that's good. Let's go head over to the code. We're going to want, I think, our friend, the calculator. And what do we want to do here? We're going to need to parse, and we're going to need to verify if it's valid. That's pretty much it, right? So let's start with the calculator tests. I'm going to structure these like I like to, so that if I group them, I group them with subclasses. So we'll start with, can you parse something? Let's go grab one line of data from here. Let's say var result is calculator parse this, and then we'll say assert equal 190 result target assert equal 10 and 19 for the result values. Okay. So there we are. That's what we're going to need. We're going to need this static parse function. So let's go ahead and let it implement that for us. The result of this is going to be long. So you might have noticed in the final value here, that is a huge value. So when I did this the first time, I sort of discovered that we were going to need longs just because I ran out of space in ints. And the runtime was basically saying, hey, you tried to add something to a number and you made it too big. So that's how I discovered we were going to need longs. So I mentioned that longs were going to come into it sooner or later, and it's here. All right, so we want this to be able to return basically a tuple with targeted values, right? So you're going to return a target and values. And we're going to take an equation. Not implemented sounds fine. Make sure these are skipped. They are. Let's go ahead and run this test and watch it fail. There we go. Method not implemented. Very good. All right, so this is a pretty straightforward thing. If we want to do you know, the simple case, right? We can return 190 and 10 and 19, force ourselves to implement a second piece of data. Okay, so that's good. Oh, I have verbose on again. Let me turn that off. Whenever you see me running with verbose, it means that there were things that were running slowly and I wanted to see how slow and whether or not I could make them faster. Hint that we might be doing some optimization today. Okay. So that's fine. Let's turn this into a theory, right? Let's say we have inline data, and the inline data is 190, 10, 19, and we expect a target of 190, and we're going to expect 10 and 19 long as our array, which it's going to say we don't know what the target type for that is, which is fine. We'll just say new long. That'll make it happier. Okay, now we're yelling. It's yelling at us because we don't have parameter values for that. Of course, we don't. So here's our equation. There's our target, and then there's our values. So now we do the equation and the target and the values. Okay, that should still run. Put in one more data point here. Let's just do this one. Inline data for that one is 3267 long, and then longs for 81, 40, and 27. Okay. Now that one's going to fail because, of course, we hard-coded the data. So now let's come back up here and parse correctly. Our friend long parse in link is going to be, in use here. So we'll take equation. We will split. Now, looking at this data, the things that separate us are colons and spaces. So let's split on colons and spaces. We have both a colon and a space here, and we don't want an empty, so we'll do string split options. Remove empty entries. All right. So we'll do that. We're going to do equation split, and then we're going to do our friend now long parse instead of int parse. And then we're going to do a to array on that. Okay, so then the first piece, the target, is going to be pieces of 0, and then the rest is going to be pieces of 1 to the rest. Okay, fairly straightforward. Go ahead and run that again. Now our tests are passing. All right, so I think we have parse. What are other interesting things we could do here, though, right? So what if we don't have a colon? What if we have non-numbers? All right, so these are things we might come back to later and add guard clauses to this because, as you typically do for advent of code, we're assuming the optimal path. We're assuming we don't have error conditions. But in real world, these are some of the error conditions that we'd want to figure out. So, what do we do in these cases? All right, so what's next then is we now need to find, is correct. That's the other half, right? So verify that it's valid. That's what we're going to do. We're going to define something that basically says, is this correct? So given this target and given these values, is it correct? Row new not implemented. Okay. And then what our tests look like, we'll go ahead and start out with a theory. Public void can compute is correct. And we'll say, given the equation, what is the expected results? All right, so we know that this one is correct, right? Because that's what it told us in the validation. So this one is correct. The other ones that were correct are 3267 and 292. So let's go grab one that isn't 3267, 192. So let's take a complicated one. Let's take that one. Okay. Inline data. that is not correct. We're just going to hang on to that for a moment. We're going to say assert equal calculator is correct. Forgot to make you static. Is correct for this equation. Oh, sorry, for parsed is calculator parse the equation, right? And then we want to make sure that the equation target, the parsed target and the parsed values are exactly what we expected, right? So we expect this to be that. Okay. We should run this. We should fail because of not implemented, and we do. So our not implemented is basically, obviously, the first version we can do is we can just return true. All right. That now passes, and this is why I picked a true and a false, because I knew I was going to do this. Cheated a little bit. Okay, and so that one is now false, is not false, needs to be false. So we actually sort of need to figure out the way to do this. So now we're down to the crux of the algorithm. And when I said in the beginning this algorithm was a little tricky, the reason it's a little tricky is because of that exponential growth, right? You basically have to go down each path. So for every number, you have to look at both plus and multiply, take the plus and multiply value and stick it back into the array, so like collapsing two values into one, and then test that value with the rest of the values in the array, right? So every time you take that step, you're turning one set of data into two, right? And so that's why it becomes an exponential growth kind of a problem. So what's the easiest way to do that? Well, the easiest way to do that is we can start by saying, we know we need to do add and multiply, right? So we'll do this. The sum is going to be values sub 0 plus values sub 1. And the product is going to be values sub 0 times values sub 1, right? So the answer here now is if the length of the values is 2, right? So we need an exit case for our exponential recursion that we're going to do. So we know that if we only have two values that were sort of at the end of our calculation, we're going to return sum is equal to target or product is equal to the target. So one of those two has to be true. And if that's not true, then that's how we escape out of this. When we have more than two values, what we need to do then is we need to take the two values, the sum and the product, replace those two values that we pulled out, values sub 0 and values sub 1, with the sum and check it, and then do the same with the product and check it, right? So here we're going to say return is correct for the target, and we're going to need a new array which includes the sum and then values sub 2, right? Or is correct for the target with the product, and then the rest of the values. Okay, so when I said the algorithm isn't that complicated, this is what I mean. It isn't that complicated. You know, from a numerical standpoint, this is pretty straightforward. It does have an exponential growth problem. And exponential growth problems are usually a tricky part of adventive code. They're the places where reasonable algorithms for brute force stop being reasonable. Don't think we're going to hit that today, but again, it's a warning sign for you to take a look at. All right, so first of all, do we correctly interpret true and false here? Let's run these tests. We do. All right, I think at this point we have enough to solve part 1 of the day, right? So for each var equation in file, read all lines of the file name. We're going to do this, which is parsed is calculator parse for the equation. By the way, before I do this, we have, like we have up here, we have other problems. It's what if there aren't at least two values, right? That's an interesting case that we need to evaluate. What if there aren't at least two values? There's probably others, but that's one. That's an edge case that we don't have to worry about in adventive code, but in your real production code, you would have to worry about that. All right, so we have this parsed, and then we're going to say if calculator is correct for the parsed target and the parsed values, then the result plus equals the parsed target. All right, so we need the addition of all the correct targets. All right, is that going to get us 3749? It helps to stop skipping. Okay, so that got us 3749. Now, if we go look at day 2 data, as you'd expect in this kind of a scenario, it's, reasonably long calculations, right? And not too many numbers, but enough numbers that the exponential problem could be big, right? So if we look at this, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? That's going to be 2 to the 11th iterations. So that could potentially take some time, 2 to the 11th. And this is also our first hint that we were going to need longs, right? This is, I'm going to put these in here, even though they can't stay in here, right? That number is 3 trillion, right? Millions, billions, trillions. 3 trillion is too big for an int. Okay, so that's another hint that we needed longs. All right, let's take that data out and let's see if that works. Okay, that does. Pretty good. All right, let's go back and look at our part 2. Okay, so part 2, the engineers seem concerned. Calibration results are nowhere close to being within tolerances. Just then you spot your mistake. Some well-hidden elephants are holding a third type of operator. The concatenation operator combines 2 digits from its left and right inputs. So 1, 2 concatenated with 3, 4, 5 becomes 1, 2, 3, 4, 5. All operators are still evaluated left to right. All right, so now apart from the 3 equations, we get some more that work. So 156, 15, and 6 obviously is a concatenation. And 7290 is 6 multiplied by 8 concatenated with 6 multiplied by 15. Okay, so we have more things that can hold up to concatenations. So let's actually take all of this data over here, and we're going to say public void can compute with concatenation. And we're going to take equations, and we're going to take expected again. Right? So this is going to be a theory. So I'm going to put some inline data here, inline data. We have 3 new samples here. So we have that is going to be true. We have this is going to be true. We have this is going to be true. But also, even though we've added concatenation, these other ones are still true and false, right? So 161011 is obviously one that is still going to be false because it's not on our list of truths. So given that, what we want to do here is we're going to start with this, and this is going to be our failing test. That is going to drive the next iteration of this algorithm, right? So let's go ahead and run this. So that's our failure, right? So that's our failure. Now we need to know the difference between whether or not we're going to concatenate or not, right? Because we go from 3749 without concatenation to 11,387 with concatenation. So we really have to change is correct to include a concatenation flag. All right, so bool support concat. Good enough, right? Whoops, that's not what I meant. And I put those in the right place. Okay. I meant to put that up here for is correct. So for the moment, we're not using that. We do need to pass it along. Okay, so that shouldn't change any of our behavior here. Let's see, we're missing passing the concatenation flag here. Are we missing it anywhere else? Just a warning for unused parameter. Okay. So we're still in the same boat, right? We hit our first test case that we now know is now missing information. So this one, we need to be able to do the concatenation in order for that to be true. So how do we do that? That seems pretty simple, right? So we can say the concatenation is going to be long parse of value sub 0 toString plus values of 1 toString. So basically, we're going to take the strings, we're going to mash them together, we're going to reparse it as a long, right? And so we need to know if the concatenation is equal to the target now. And then the third thing we need to do is we need to recall with this target and concatenation and values sub 2. But we only want to call that if we know that we're supporting concatenation, right? There's really no point otherwise. So if we support concatenation, right? And then same thing here. We only want to return this as being valid if we support concatenation. Whoops. And the way that we can sort of make this show up as being a value that we're testing here, right, is we can now test this value to be false. So here, where the concatenation is false, we know that that should be false. And here, where concatenation is true, we know that that should be true. Okay, so let's go ahead and run that. So those tests are now working. I expect for us to be able to do that, and then those tests will be working. Okay, that's good. So let's come down to day 2, and let's unskip this, and let's see if we get our 11,387. Oh, nope, we need to, write code. All right, you're going to be concatenations. Okay, so you're good. And then here we're going to run this, and let's see how that comes out. And you can see we took just a little bit amount of time. It wasn't that bad, right? Our total runtime here is a half a second, but we did actually hit the correct answer. And this is where I put in the timing with verbose. So I wanted to see exactly how long things were taking. All right, so if I do verbose now, we'll see that down here, this half a second is really sort of the outlying problem. And so why did we go from part 1 with data being 29 milliseconds to half a second? Why did we do that? The answer is the exponential growth, right? We went from growing 2 to the power of n to 3 to the power of n, right? So our exponential growth is now to the power of 3 instead of the power, or 3 to the power of n instead of 2 to the power of n, right? So, when we saw 11, let's bring up my calculator. I think we're going to need, we have powers here. We don't have superpowers there. Let's do scientific. We need x to the y. Okay, there we go. So 2 to the 11 is 2048, right? But 3 to the 11 is 177,000, right? That's what we mean by exponential growth. And so if we went from 2,000 iterations to 177,000 iterations, kind of makes sense why we're taking a whole bunch of time. So the first thing we can do now is let's go ahead and skip a bunch of this stuff. We can skip, not now. All right. Let's skip some of these tests. So we're really focused on day 2. Actually, we can leave part 2. We can leave part 1 in there. Let's just get the timings for part 1 and part 2. We're still doing the can parse. Let's get rid of that. I missed that? I guess I missed that. Oh no, skip, skip, skip. Oh, I thought something was running there. Shouldn't have been running. Oh no, this is just starting skipping. Okay, so here's our timings, right? We have 29 milliseconds and 450 milliseconds, half a second. So what are things that we can do to help cut time down? Right, if we look at our algorithm, one obvious thing we can do is we can say that if you have already exceeded the target, there's no sense continuing down the path to try more operators, right? Because all of our operators, at the very least, do not decrease value. There is some instances where we will see 0. I don't know exactly where they are, but there could be some instances here where we would see 0. So the reality is that we should only call this if, in particular, for example, sum is less than or equal to the target, right? If sum has already exceeded the target, then that's no deal, no good. And then here we do the same thing, less than or equal to the target, right? And down here we can just say concat, less than or equal to the target. All right, so that's one optimization we can do, right? Let's make sure we didn't break anything. We did not break anything, and we went from half a second to 316 milliseconds. That's pretty good, right? We literally cut a third of the time off of the algorithm just by knowing that there is a case where we can drop out. There's probably more optimizations we could do, like this, right, is creating a new array every time. So not only we're doing exponential growth for, the calculation time, but we're also doing exponential growth for memory allocation, right? So how could we do it so that you could say, here is a value and here's the rest of the values, right? So we could make a version that looks like this. And we'll say values, and we'll say the first value and then the rest index. Okay, so that's basically saying, tell me what the first value is, right? Because here's our first value. And then here's what the rest of them is. And so the rest of the index here is 2. We know that. So if we knew that, then what would this algorithm look like? Let's just go ahead and copy this down here. Let's say now we don't have value sub 0. Everywhere we see value sub 0, that's the first value, right? So our first value, and then our second value is going to be the the values from the start of whatever is the rest. So value sub 1 is that. Okay, so far so good. That gives us our first value and the rest. And then down here, instead of calling is correct with this, what we're going to call this is our first value is the sum, right? Now we need the values, and then we need the sum, and then we need, so this is 2, that's rest index plus 1, rest index plus 1. Okay, so now let's take that. Here we'll do values product rest index plus 1. And then here we're going to do values concat rest index plus 1. Okay, so this algorithm we could call from this algorithm now, right? This one doesn't have to be public. This one can be private. And here we're just going to say, just give me is correct support concat target values. The first value in this case would be value sub 0, and the rest index will be 1. That's how we'll start that. First of all, does that work? Did we break anything? We broke things. Index is outside the bounds of the array. Okay, so something I missed. Let's go look and see what I missed. Oh yeah, values length equals 2. So that's not correct anymore, right? So we need to know when to stop. So if the rest index plus 1 is equal to values length, right? So if we have seen all the values just by looking at rest index, then we stop. That should fix that, right? Okay, so now you can see that all of our data is still working. We have now gone from 330 down to 175. So clearly memory allocation was half of what we were doing there. So we've gone from half a second to 1/6 of a second. So that's a pretty good optimization. Those are pretty good changes. Now we can come back here and we can get rid of all of our not nows. Let's get rid of all of those, right? Let's get rid of all those. And run all of our tests, and they all run. And now instead of half a second, we're down to 1/4 of a second. So that looks pretty good. Okay, so normally we would be done here. We could call it a day. But what I wanted to do was we made some notes for ourselves about sort of edge cases. So in parse, what happens if we don't have a colon, right? So let's say public void must have target. Okay, so what's going to happen if we say calculator parse of 142.12? Right, what is the answer going to be for that? We probably want that to throw an exception, right? So we'll do this. EX is record exception. Okay. Assert not null, this exception. Assert is type. We want to probably call this an argument exception. Right, and then we could say, you can get the value, the casted value out of this. This thing is called equation, right? So that would be arg_ex.param name. And then we can do assert equal, I don't know yet, arg_ex message. So I don't know what that message is going to be yet, but for now, we know that that is going to fail. I'm going to turn verbose off because we're done looking at timings, and it just makes a bunch of noise. So now we have this one failure where the value is null because we didn't throw an exception. All right, so if we really want to know this, like we know that this is a fairly optimal way to parse this, but the other way we could do it is with a regex, right? And our regex would look, let's go back to our .NET regex tester. There you go. And if we had 1, 2, 3, 4, 5, right? So we know from a regex perspective, what we want is at least 1 digit, right? And then we want a colon, and then we want a space, and then we want at least 1 digit. At least 1 digit. Okay, so that's going to be the first one. So how do we have one or more of these? We do a plus, right? But do we have to put that whole thing in a parenthesis to get that to happen? I don't remember how to do that. All right, let's Google this. Regex find repeated pattern. Okay. Yes, upgrade your browser. Sure, whatever. Regular expressions for repeating sequences. Okay. Oh my God, necessary cookies only. This is not the browser I normally use. So of course, everything's going to pop up and say everything's terrible. I've written it like this, but what I really want is like this. $$. So that's from the front, from the back. I don't care about that. Given character, sure, 3 times. And then do that over and over again. Then do that over and over again. Okay. So we do it like this. Then do that over and over again. That's interesting. Oh, it's not a comma, right? We need a blank. Is it blank or is it space? It's space. And then we really only want the numbers. Okay, there we go. So that looks good. If we look at it in the table, we'll see that group 1 is going to be the 1, group 2 is going to be the 2, and group 3 is going to have multiple captures for 3, 4, and 5. So we'll have to look at that, but this looks like the regex we want if we want to do it that way. So regex is going to be new. Okay, type with an N. New regex. Actually, let's do this. All right. And then we're going to do a regex match. All right, we're going to say if not, regex match the equation. We're going to throw new argument exception. Did not match equation pattern or equation. If not regex match, we need to take the match. Is success. Okay, that's all we actually have to do right now. Interestingly, we could do more. We're still using this to actually parse the values out. We're just doing the regex to validate it, but we can pull the values out here in a second. And what are you telling me to do? Converted generated regex. That's okay. We don't need that. So if I run our tests now, what we missed is the message did not match equation pattern, and then we've got parameter, and then we've got more stuff here. So here's now a tip. We can't see the whole string. We only see part of the string to begin with. If instead of letting the string comparison happen, if we treat them as objects and rerun it, what we'll see is we don't get markers anymore, but what we do get is the whole string. So this is our message. This part of the message isn't interesting to me, though, because we already tested that up here. And as it turns out, if we were to run this in .NET Framework, what you'd find is this part of the message is different because they've changed the way argument exception formats this between .NET and .NET Framework. So what we're going to do instead is we're going to do a starts with. Oh, stop that. All right. Okay. There we go. So we have that working. So we must have a target. How about must have values? Public void must have values. Let's do this again. We'll say 42. Okay. So there's that. That works, but also we have, what if we have non-numbers? I think we will be able to test that really easily with this regex as well. So we've tested what if we don't have a colon. We should also test, we'll test this as an inline, because we have another version, right? Inline data. I'm going to parse the equation, right? But another one that looks like it's probably wrong is this with just one number is probably wrong, right? Because we talked about what if there aren't at least two values? We put it down here, but that could be a parse problem, right? So right now, that's not failing because our regex allows you to have 0 or more of these, but what we really want is 1 or more of those. Okay, so we'll change the star to a plus. And now we have that. And then the last thing we need to do is what if we don't have numbers? Okay, so let's say 2112 ABC. Okay, what happens then? Okay, that still fails because the regex is still saying, by the way, we need those numbers. Okay, so the last thing we could do, but we're not going to bother with, is we could stop using the string split here and just pull the values out of the regex. but we know how to do that. We've done that before. Doesn't feel like something that we need to cover. So I think we've covered all the edge cases that we wanted to cover now. So this is looking pretty good. I think I'm pretty happy with this. Like I said, I would change this to use the regex to pull the values out. We have a test that would actually, let's do it. We have the test that'll let us do it, right? Because we've already looked at parsing here to make sure that we actually get the numbers out correctly. Okay, so let's do that then. Let's stop here with valid data so that we can look at the match, so we can figure out the easiest way for us to peek inside the match. Okay, so there's 10 and 19. So for groups, right, we have group 1 is going to be our target, right? Group 2 is our first value, so that's 10. And then group 4 is going to be our values for the right-hand side. So we need 1, 2, and 4. So target is long parse match groups 1 value. First is going to be long parse match groups 2 value. And then the rest is going to be match groups 4. And then the groups value is a string. Captures, right? Captures. And then we're going to select our long parse again. And we're going to turn this into an array. Captures is a what? Oh, right, I remember. So captures is capture collection, right? And a capture collection is a list of captures, but because the I enumerable isn't generic, we need to convert that into a capture. So we're going to do cast capture. And then we're going to select the value for our long parse. Okay, and then that should get us that. So let's stop and run again, and let's see if we're happy with where that came. I don't care about that. So our target's 190, our first is 10, our rest is 19. So far, so good. Okay, so let's go look at our equation. Our equation is same thing. Let's do this. Let's do equation, target, first, rest. Okay, so that's okay. So here we have 3267 as the target first, and the rest is this. I'm not super fond of this first and rest thing, but I think if I put capture around, I don't know if I could do that. No, I don't think I can do that. But all right, so we don't have to do this anymore. What we can do is we can just return the target and then first and the rest. That should be good enough. Do all of our tests still pass? They all still pass. So now we're using the regex to actually pull the values out instead of redoing a string parse. Is it faster? Probably 6 of one, half dozen of the other. But that's the way it goes. All right, I think we're done today. I think that was a pretty good amount of refactoring, and now we're starting to test some edge cases, which we really haven't done before because time didn't really allow it. And today I got to the problem quick enough that I felt like we could spend a little bit of time talking about edge cases. So people who just wanted to sort of see how I got to the solution can drop off, and then everybody else who wanted to see the actual handling of the edge cases is here. This is not the order I would have done it in, right? Because I wanted to let the people who just wanted to see the solution get there and then get out. Normally I do my edge cases first, right? It's easiest to do guard clauses. Like, for me to look at, for an example, what happens if I pass an empty string? By the way, this test and this test is the same, right? So all we have to do is we could bring this over as a piece of data. Right. One day I'll remember I copied the quotes. And then other things that are interesting, like what happens if you pass an empty string? What happens if you pass null? All right, these are other things that we could do. Oh, it doesn't really know this. So we'll do default of string. And then it's going to complain that null should not be used for string. Use a non-null or convert it. So that's why we'll use this and whatever. Or we could bring the equation in as nullable and use the bang operator here and see what happens. Right? So then we don't need this test. You know what? It occurs to me as I'm doing all of this that I wasn't showing you my screen. That's amazing. So you can see I've collapsed those two tests into one. And I've done default of string here. I've done empty string. I took that 142.12 and put it over here. We can see what's going on here. We expected an argument exception, but we actually got an argument null exception because when we pass null. So then the question is, should we because we're getting an argument null exception from this match, right? So we could fake it by basically saying, here, if they gave us null, we're going to use string empty, and then we'll get back to having the error message that we want. That was the easiest way for us to fix that. So here we go. We've now collapsed those two tests down into one. We've added a couple more edge cases. But anyway, as I was saying, when I did some work off screen that you couldn't see, sorry about that. I like to do the edge cases first. So I like to do the null testing and the empty string testing and the bad data testing. I like to do those first, get those out of the way, and sort of leave the, the real test or the real tests, depending on how complex the thing is, for after I do all my edge case testing. But like I said, I did it in inverse order today because I wanted to get right to the answer so that people could drop off if they weren't interested in the rest of the TDD stuff. So anyway, that's it for today. Hopefully that was helpful, and I guess we'll see you tomorrow.